Welcome to Chemistry with Mrs. Schroeder. We're here today to talk about ionic compounds and how ionic bonds form. Our objectives today are just to describe the process of forming this ionic bond and to explain how the properties of ionic compounds depend on the nature of those bonds. Opposites attract. If you look at magnets, the north attracts the south. If I put the south and the south together, they're going to repel each other. They won't want to attract. So when we're talking about ionic compounds, we're talking about things that are attracted because they are opposite charges. So ionic compounds will form when ions, which are things that have a positive or negative charge, when ions that are opposite charge are attracted to each other. This happens when electrons are transferred. Remember the gain or lose of electrons is what makes an ion. When I do transfer those electrons, it does require energy, and we'll talk more about energy in class. But ionic compounds are not considered molecules as such. Instead, we're talking about ions that are surrounded by other ions of opposite charges, and they exist in crystals. Overall, the ions exist in ratios that balance the overall charge to zero. So if I have a salt crystal, it won't have a charge overall. It's going to have an overall charge of zero because things are balanced out. Covalent compounds we'll talk about in Chapter 6. These are other kinds of compounds that form when atoms share electrons. So covalent compounds are shared. Again, this is Chapter 6 that will cover covalent compounds in a lot more detail. So a couple examples of ionic compounds. One of these is sodium chloride, very familiar table salt. If I looked at it under a microscope, I could see this crystalline structure. And if I were to look at it, another one, calcium fluoride, would look, and depending on what's in it, it could have different colors, but it has a different type of structure. It has to do with how many are around it. So if I look at my sodium, here we go. Okay, my sodium is actually not yellow. My sodium is supposed to be in pink. So my sodium is in pink, and my chlorine is in, oops, green. It is green. Alright, so when I look at this picture, if I were to try to pick out one of these, let's say I pick out this particular pink one in the middle, and I say how many are surrounding it, I would actually count up 1, 2, 3, 4, and then there's one coming out at us, 5, and then there's 6. So there's actually 6 ions surrounding it because of the way it's set up and the way it's ordered in its crystalline structure. So the crystal structure depends on the size and also the ratio of the ions. If I have a ratio like calcium fluoride, CaF2, its structure is not going to look like this structure because it has a 2. It's got, fluorine is much smaller. It's not going to look like this because fluorine is the smaller one now, so it's going to have a different structure, which is why they look different when you look at them on the outside also. And here's my picture with my yellow and green pictures. But a crystal lattice is a regular, infinitely repeatable pattern in which the crystal is arranged. So I could continue making this pattern if I were to continue, if I had more sodium and more chlorine to continue throwing into this crystal, I could make it bigger and bigger and bigger by going off of all of these sides with different, or with more ions, if I had them. And this is the calcium fluoride structure. It looks much different. It's got much more triangular arrangement because for every calcium is the red ones, there's 2 fluorine around each one to balance the charges out. So I have to have many more structures, or many more, a much different structure to it. But again, I could continue making this one bigger also by adding more calcium and more fluorine ions. The unit cell is the smallest portion of the crystal structure that still shows the three-dimensional properties of the entire lattice. So something like just Na to Cl is not a unit cell. because it doesn't show any three-dimensional structures. This could be a unit cell. It's showing that it's different than the calcium fluoride structure. They're showing something about the three-dimensional arrangement of those atoms. Transferring electrons does involve energy, and these are terms that we've talked about last chapter. Ionization energy is the energy to remove an electron. Electron affinity is the energy which changes when you gain an electron. You can see there's energy gained. And the book shows you this chart. For now, just write down the ionic bond forms when the overall energy of the ionic compound is lower than the energy of the elements. So energy is on this side. If this is where we start, we have different steps that add energy to it, and then different steps that are releasing energy. And this is the end down here. If this is lower, then a bond will form. If this end ended up somewhere up here, the bond is not going to form because it overall takes energy to maintain that position. So all things in nature want to go to a lower energy, and that becomes more stable if they can get rid of energy. And we'll talk about energy some more in class. Ionic bonds are very strong. They're very, very strong bonds. This attractive force of the positive to the negative charges gives it very, very strong, a strong bond, which means strong properties. If the bond is strong, it's going to take a lot of energy. So a lot of energy to break the bond, which is what gives it a lot of its properties, which we'll look and read about in class a little more. But things like a high melting point, things like they're brittle. I can't really bend them closer together because then I might displace and put positives next to positives. So they'd rather, they're brittle, they'll shatter. If I try to bend it, it will tend to shatter. And as a comparison, if I look at my ionic compounds, I have melting points 1,000, well, look at the degrees Celsius, 1,261, 800, 748. These are all ionic compounds versus our covalent compounds, which have melting points anywhere from 27 degrees, which is a little warmer than room temperature, to negative 182 is methane gas, which is a gas at room temperature. So covalent compounds tend to have much lower melting points. Covalent ones are much higher because I had to put the energy in to break those bonds between adjacent ions in order to make it melt. And we're going to go through this in class. So tonight, when you get a chance, look at identifying ionic compounds on page 173. Read through the skills toolkit. We're going to work on creating a flow chart in class of how I could identify ionic versus covalent compounds.